Good morning. I'm Dick Seitz, and I'm going to talk about KUtrace for RISC-V. I'm going to talk a bit about what kernel user tracing is, and then a bit about a RISC-V implementation on the unmatched board. So kernel user tracing is a software microscope that records every transition between kernel mode and user mode execution. So every system call, system return, every interrupt return, every trap return, every context switch, and makes a long trace of all of the events in order. So no profiling, no aggregating, and does all this on other machines with less than 1% overhead. I'll talk about the unmatched board overhead in a little bit. So it's a small set of Linux kernel patches. It's about 150 lines of code total for the patches that call out to a loadable module, and then everything else is done in post-processing. So this is the picture with the few lines of kernel patches, control program to turn tracing on and off. There's a loadable module that actually writes the trace to a reserve memory and kernel memory, and then everything else is post-processing. This is an example of the events that are recorded. There's 4 CPUs here, 0, 1, 2, 3, and 4. And this timeline shows transition here of doing a system call, returning from it, actually doing another one, but it's overlapped, returning from that system call. So all of these little green triangles are the events. There's not very many of them. And they're 20 bits each. I'm sorry, they're 32 bits each. There's 20 bits of timestamp and 12 bits of which event, which system call, which interrupt, etc. I post-process those transitions into levels of this CPU 0 is executing the idle loop and then spending 30 microseconds. This is on an Intel x86, 30 microseconds coming out of idle. And the tall multicolored timelines are kernel code, and the half-height ones are user code. And the various colors delimit system calls, interrupts, and faults, mostly page faults. So I'll give a couple examples. This is a full 4-processor trace of Hello World running over SSH. So the incoming thing here is an Ethernet interrupt on CPU 0 that starts up another process, that starts up another process, that starts up what turns out to be the command line interpreter, which clones itself because the input says /hello, and does an exvc, and eventually runs the hello main program over here, does its 12-byte write of hello world carriage return, and that whole works takes 4 milliseconds. But you get to see exactly why it took 4 milliseconds instead of something much shorter. And of course, in a large data center kind of environment where I first did this, you get to see the real reasons for long tail latencies on production computers. I did this originally at Google. So this particular trace, there's actually 6 different processes involved. The SSH daemon gets the interrupt, calls a kernel worker, calls bash, bash clones itself. You get a second copy of bash. You run hello, there's a Linux read copy update thread that runs for a little bit, and another K-worker thread. This is a zooming in on just the beginning of the hello world main program and the end of the main program. And what we get to see at the beginning is an instruction fetch page fault, a load page fault, a store page fault, call to fstat to see if standard out is actually open. A couple of break calls that extend the stack, another page fault. We finally get to the write, which writes 12 bytes, and then this inserted marker says the end of hello. So I just put this in as the last line of the program, which is all of 3 lines. And this write wakes up a kernel worker, which wakes up the SSH thread, which sends out a write off the end of the screen. So the big time sinks in this trace are the clone call takes 583 microseconds. The execvc VE call, whoops, back one, takes another 600 microseconds. And there's a bunch of going back and forth. But there's also, if I search for page, there's 138 page faults, and they take 1.3, 1.4 milliseconds. So the page faults actually take more time than the sum of the 600 microseconds here and 600 microseconds there. That's the kind of thing that's not in the pictures in our heads. More time is going to page fault than going to the system calls that you expect to see. And when you're looking at tail latency in large, I did some consulting at Tesla for Autopilot 2.5, or if you're looking at large data centers, this gives you exactly what's going on, what's causing tail latency. So to gather the trace data, the timestamps are important, and that was the thing that I had a bottleneck for with the RISC-V Unmatched board. So I'm going to talk about the unmatched timer implementation. And there are other chips, other boards, which I did not have access to. But the fact that this one was so difficult suggests to me, and I'll suggest on the last couple of slides, that the architecture group really needs to pay more attention to timers. So I started with an unmatched board, and I just wrote a little program that does a CSR read of the cycle counter, does 4 of those, and then prints them out, and looked at the compiled code assembly language to make sure it really was read into 4 different registers. No other instructions, just read. And the output after reading them, I get 829, 830, 831, 832 at the end. So from that, I learned that CSR cycle, in fact, counts once every cycle and takes only 1 cycle to read. So I moved on to looking at the cycle counter, the time counter, and the instructions retired counter, and then did a loop that goes around 1 million times and takes about 4 milliseconds, and then read those counters again along with get time of day. And the output looks like this. The get time of day start and stop. When you subtract them, there's 4.2 milliseconds of doing this 1 million loops. The cycle counter incremented by 50 million. The time counter incremented by 4,202. So we learned from that the time counter is counting exactly once per microsecond. And the instruction counter counted 50 million instructions. I'm sorry, 5 million instructions. The cycle counter is 5 million. So we're seeing that the instructions are executing at 1 per cycle. The time for the cycle counter is incrementing 1,196 times per microsecond, which is the 1.2 gigahertz rated speed of that chip. So this is all looking good. Things are consistent, and we're getting 1 instruction per cycle. So then I ran 4 copies of that program and found that on the 4 different processors, the cycle counts differed. This is in the seconds column. They differed by tens and hundreds of seconds, so they were not in sync. The elapsed time for all of them was 12 billion counts, which is the 1.2 gigahertz times about 10 seconds. So that means that I can't use the cycle counter to timestamp events on 4 different cores and line them up in time. I thought, maybe I can calculate the differences once, and then the differences will remain constant, and I can use the cycle counters after all. So I did another loop of just get time of day, doing a loop, but inside the loop, sleeping for 4 milliseconds at a time. And each time reading the cycle counter and the time counter and storing them in an array and doing that, 256 times. And so we get the start time, the stop time took a second. The cycle counter, delta was what I expected, but the time counter ratio of time to cycles is no longer 1,200 per microsecond, but only 10 per microsecond. So what I learned from this is during the nanosleep, the cycle counter doesn't count at all. So that means even if you got the cycle counters on 4 cores in sync, as soon as they waited different amounts of time, they'd be totally out of sync. So the cycle counter is useless for high precision tracing of exactly what's happening on each CPU core. So I switched to looking at the time counter on the unmatched board. So I did read the cycle counter, read the time counter, cycle counter, time counter, cycle counter, time counter, and print it out. And what I found was cycle counter, between these two reads of the cycle counter, this read of the time counter took 452 cycles. Reading the cycle counter took 1 cycle. Reading the next numbered CSR, the time counter, took 452 cycles. So the second time, 432, 405. So it's 300 nanoseconds. This is because the time counter is literally implemented as a physical memory address, and the CSR actually traps and goes off to this hidden code that can access physical memory and trap back out. And so that means the overhead just to read a timestamp is way too high. I mean, it's 300 nanoseconds. So that means if I'm trying to time a system call that takes about 100 nanoseconds, I'm spending 300 nanoseconds at the beginning edge saying, I entered the system call, here's the timestamp. Another 300 nanoseconds at the trailing edge saying, I'm exiting the system call, here's the timestamp. Hopeless overhead. And in addition, the cycle counter only increments once every microsecond. So if I actually time a 100 nanosecond system call, it either takes 1 microsecond because there was an increment in that time, or it takes 0 microseconds because there is no increment in that time. So I found that really discouraging for being able to see exactly where all the time is going. So what's needed to get good timestamps, and the thing I want to sell to anybody here designing chips and also to the architecture group, is you need a timestamp that has known units. Preferably nanoseconds. Known units means I read something on some Intel chip, I read some time of the cycle counter, the RDTSC counter. I do some work, I read the RDTSC, I subtract and get a difference of, say, 423. 423 watts. Nanoseconds, microseconds, minutes. There's no units to the cycle counter. In fact, if it's a chip that was advertised as 2.8 gigahertz, those units are actually 2.8 gigahertz. But even if the chip was running at 800 megahertz or running at 3.2 gigahertz overclocking or turbo or whatever, the number that was printed on the package is the units, except there's no way to find that reliably underneath Linux or anything else. So having the known units is important. Having nearly the same value across all the cores, and I'll get to what nearly means on the next slide. And a resolution of 20 microseconds or so is useful, and close to 1 cycle to read. And the ARM 8.6 architecture gets this right. They say, and I quote from the manual, that when the system counter is up and running, time must not go backwards when device A reads the time, communicates it to device B reads the time. If time goes backwards, then you can never correlate stuff well. This used to be a problem when I was at Google early on, when the Google file system, when it observed time going backwards precisely because of this, it would crash. And what Google had to do at the time was whenever a CPU slowed down, they had to turn off the cycle counter read, and then when that subsequent read trapped, they had to go get the clocks synchronized and then let the read happen. The other thing that ARM 8.6 and later gets right is they say that the units of the counter are fixed. They're nanoseconds. It doesn't mean that you have to increment it by 1 every nanosecond. You can increment it by 10 every 10 nanoseconds, 20 for any 20 milliseconds. But they also recommend that the resolution be no worse than 50 megahertz, once every 20 nanoseconds. So it's okay to have a slow counter. It's okay for it to change while if you're low power, you can drop it off. Incrementing by 50 every 50 nanoseconds is below the ARM recommendation at only 20 megahertz. But for some of the chips here that are really embedded processors and stuff, and they're only running at 800 megahertz or gigahertz or something, it would be okay. It would be commensurate with what we're actually trying to measure. So my summary is that I like the RISC-V community and the architecture group and the implementations to look at an architected system counter that counts in known units, that has nearly the same value across all the cores, within this communication delay between cores, doesn't go backwards, has a resolution of 20 nanoseconds or better, and is close to 1 cycle to read. If it takes 30 cycles to read, there's too much distortion when you're doing lots of transitions close together. And it needs some checking of implementations that they are following the architecture if this is architected. That's all I have. I've written a book that talks about using tracing like this, and the patches for RISC-V are up on GitHub. There's a much longer version of this talk that I gave at Stanford last March, and this is the ARM architecture manual that I was quoting. So that's it. Let me take a few questions, and then we'll move on to the next speaker.
Yeah, I was going to ask you real quickly. Isn't that resolution tied to the frequency of the processor to some degree as far as what you need, right? I mean, you need to be able to sample at a frequency that's going to give you enough details, but given that the processor is going to vary in frequency across all of the pieces, dictating a minimum is sort of capping how fast processors would go in the future, right?
Well, it's tapping how slow they could go in the future.
Or how slow you go. Okay, yeah.
I mean, there's nothing that says you're not allowed to count at a gigahertz. It's just saying that it's more useful if you count at least 50 megahertz,
right?
Which is often not a problem, but certainly around 20 megahertz for very slow embedded chips.
Yeah. Cool. All right.
Other questions?
Yeah, I love this. I love the pictures. I have friends that would die for those graphs.
Thank you. I mean, it's probably here is more software guys than hardware guys who should be addressing this, but V8, I mean, 8.6, is it anything implemented on this? Because I think V8.6 is like a proposal for ARM. I didn't see a chips with that version yet. But just a comment.
Yeah, I don't know the answer to that.
It's 8.6. It's V8 is.
I'll make one observation. I'm the reason that spec exists.
Okay.
Let me repeat
I think that's a
that.
great talk, but it's really very fundamental things which should be addressed by architecture level. I fully agree.
So John Masters was making the comment, he's the reason that the ARM spec has those good words, which I didn't know, but good to see you here.
All right. More questions here.
More questions. In the back.
Yeah, here we go.
Trotting back with the microphone.
Thank you. Thanks. Could you please elaborate why reading the cycle count would give different counts if the frequency is maintained?
It's possible to build a cycle counter that counts once per cycle and which counts more slowly when the CPU clock is slowed down, for instance, to save power. It's also possible to build what's called in the industry now a constant rate cycle counter that always counts at the same frequency independent of power saving. The second one is much more useful. I'm not sure if that answers your question.
Okay.
Over here?
Yeah. Are you familiar with the SSTC extension? This adds some supervisor level accessible registers, which should help with the trapping, although not necessarily with any memory access latency. And as a related question, do you need access to the timers in user mode, which this extension doesn't add?
I'm not familiar with either. I only had access, this was last March, to the Unmatched board. But again, if some chip has an extra counter that's useful for this, terrific. But if it's not architected, you can't write software that gets embedded in the Linux main upstream that can be used on all RISC-V processors to see what's going on. That's my real goal.
Okay, we do have one question online. How well or bad Can your requirements be aligned with power and thermal management? I guess I would rephrase it as, is there any correlation? Are there any similar interests in this space?
Yeah, if counting at something like 20 megahertz is a power drain, I don't really know what to suggest.
Yeah. Okay.
I mean, there's some incoming clock that must be that order of magnitude. Just count it.
Yeah. Okay. Well, we're out of time, folks. Let's give Dick a round of applause. Excellent talk.
Thank you.